Hello, it's Paul Beckwith again. I'm going to continue my discussions on elevation-dependent warming in the mountain regions of the world. Okay, so this is an effect which is not as well understood as the latitudinal dependent warming or Arctic temperature amplification. So it is happening on in most mountain regions. As you increase elevation, you get more warming. It's very significantly happening in the Tibetan Plateau region, the region known as the third pole, where we're rapidly losing high altitude glaciers, and this is going to have a huge impact on billions of people that rely on water from all of the rivers that are fed by glacier melt from the third pole. Okay, there are some mountain ranges where we're not seeing this effect of an increase of warming rate with elevation. There's actually some where there's a decrease with elevation. There's some with no significant gradient. And there's some where there's not really a change with elevation, but there is some bump up at some certain intermediate elevation. So continuing from the previous video, these plots are all from the around the Tibetan Plateau. Okay, so we've got different stations. These are low-level stations, and they don't see much of a change in temperature. Okay, I mean the rate of temperature change is pretty constant, and as you go to higher elevation stations, what we're seeing is that the higher up you go in elevation, the faster the temperature trend, the warming trend is in degrees Celsius per decade. So this is analogous to going closer to the Arctic, for example, where the warming increases with latitude. In this case, you go up the mountain and the warming rate is increasing at the higher up you go. Okay, but it's not a linear change. Okay, so started talking about some of the mechanisms of it. Like there's the albedo effect, cloud effects, water vapor considerations, black body emission considerations, and aerosol considerations. Okay, and what this can do is these effects, when you combine them all, they can cause an increase in warming as you go up in elevation. And I'm going to talk about some of the details that are mentioned in this paper. Okay, so the albedo, hypothesis and mechanisms for elevation-dependent warming. Okay, so albedo is a well-known one for latitudinal temperature amplification. Right, it's an important positive feedback in Arctic amplification, but it's also relevant in snow-dominated high elevation regions. The seasonal timing of snow cover varies with elevation. Maximum warming rates commonly occur near the annual 0 degrees Celsius isotherm. Okay, so in the Swiss Alps, for example, the daily mean 2-meter temperature on a spring day, if there's no snow cover, the temperature will be 0.4 degrees Celsius higher than if there is snow cover in that region. Okay, so you can look at the altitude, the elevation at one side of the mountain, for example. There's no snow. You can get the mean temperature. Just go short distance away where there's snow, compare the differences. And, okay, so the snow reflects away sunlight, makes the surface less dark. There's higher albedo, so there's less absorption onto the dark surfaces. There's less warming in that region. Okay, the current snow line is retreating to higher elevations as the overall climate system warms. Okay, the elevation dependency of snow cover duration and also of the snow-rain ratio is nonlinear. So the rate of snowline retreat may increase as temperatures rise. In other words, the snowline is moving up as we get warming, but it's a nonlinear amount. So it can jump up in some cases as temperature rise. Okay, this will, as the snow line is moving, it causes large increases in the absorption of light at that particular region where the snow used to be and no longer is. So that will cause an enhanced warming at that elevation. And as the snow line moves up, the effect moves to increasingly high elevations. And this is a similar thing happens through greening, through the tree line. Okay, so that's the key factor, which is what we're showing here. There's a pulse of warming here, where the snow line has moved, bracketing where the snow line was and where it is now, and also the tree line. So you get this pulse of warming. So this is the albedo effect. Now clouds. Okay, cloud changes are also very important, particularly in high elevation regions, okay? Because changes in cloud cover and cloud properties affect both the shortwave and longwave radiation and thus the surface energy budget. Okay, they also affect the warming rates in the atmosphere through condensation. Okay, a band of enhanced warming caused by latent heat release is expected near the condensation level. Okay, so as you go up higher and higher, there's water vapor in the atmosphere. As you go up higher and higher, the air is cooling and you reach the condensation level where the water vapor condenses out into droplets to form clouds. And that releases latent heat. Okay, so depending on where that happens, if the elevation of the condensation level is changing over time because of climate change and global warming, that can cause an enhancement of the warming at higher elevations. Okay, and also, the clouds, whether they're at day and night is important, etc., etc. So water vapor and rate, so that's this guy here. So if this is the original condensation level has moved up because of warming, right? So the water vapor used to condense out here, releasing the latent heat, and now it condenses out here, releasing the latent heat. So the latent heat is released at a higher altitude, so that moves the warming, that warms up the air at the higher elevation. Okay, water vapor. This is the original amount of water vapor in the atmosphere, and we're increasing the amount of water vapor. Then that causes the water vapor is a strong greenhouse gas, so that changes the absorption, the elevation at which the energy is absorbed, and so that can cause heating at higher elevations here. Okay, so there's different processes here along an elevation gradient expected to lead to elevation-dependent warming. This is the sensitivity of downward long-wave radiation to specific humidity. Okay, so basically, the shortwave radiation, the sunlight hits the surface of the Earth, causes warming. The heat or the long wave radiation is radiated out, and some of that radiation is absorbed in the greenhouse gases. So if there's more and more water vapor in the atmosphere, and the water vapor concentration changes with elevation, then that will change the warming with elevation. So that will cause greater warming at higher elevations. Small water vapor increases can have a big impact if you're not in a saturated condition. Okay, so it talks about the changes in in the Alps and the Rocky Mountains, etc. Okay, the shape of the black body radiation curve. The functional shape of black body radiation curve can also change, so you can get it goes as the Stefan Boltzmann law. The outgoing long-wave radiation is one of the major mechanisms through which the land surface loses heat. It's proportional to the fourth power of temperature. So for a given change in radiative heating, higher elevations will experience enhanced warming rates because the initial temperature is smaller. So what it's saying is that the warming rate, where the temperature is much, much lower already, then the warming rate can be larger just from the nature of this effect, black body radiation effect. And then the aerosol loading issue, for example, atmospheric brown clouds and associated black carbon in Asia. It's concentrated at relatively low elevations, below 3 kilometers. So that would decrease the flux of shortwave radiation to lower mountain slopes. So in other words, if you're at low elevations and you've got all this aerosol in the atmosphere, then less light will penetrate to the surface at these low elevations, so the temperature will be suppressed, the surface dimming or global dimming. Okay, but this has a limited or no effect on higher mountains above the polluted layer. They're getting all of the sunlight. Okay, so this, now, how high do the pollutants get in the mountain regions? Well, it depends on the time of year. High levels of black carbon have been found at 5,000 meters in the Himalayas during the pre-monsoon season, but it's unclear whether such conditions reflect local up-valley transport. So is it wind blowing up through the valleys, carrying this dust, black carbon? Aerosols are transported to elevations above 10 kilometers over Tibet and much of Central Asia during convective monsoon activity. Okay, so during the monsoons, when the middle of the monsoon season, when the surface is heating up rapidly, and this, so there's a low pressure area, the hot air is rising, there's a low pressure area over the surface, it brings in moist air from the Indian Ocean, for example, and you get a huge convective uplift, and it's bringing up black carbon to very high levels in that case. Okay, so so there's all of these different effects that are going on. So when you combine them all, the resulting response and the interactions are complex. Some factors will be more influential than others in certain parts of the globe and at certain times of the year. And this may partly account for the differences in elevation-dependent warming. Okay, so basically, this is a more complex situation than the Arctic temperature amplification. Okay, in most mountain regions, certainly in the third pole, as you increase elevation, you get more warming. And the factor can be a factor of 2 or 3 times higher. There's some regions where the opposite trend is seen, and there's some regions where there's no trend seen. So there's a lot of different factors that play into this. Okay, so which one dominates is, it depends on the region. Depends very much on the region. Okay, so the big problem is, in theory, it should be simple to document the rate and geographical pattern of warming with elevation over recent decades. But in practice, it's very difficult because long-term meteorological stations with more than 20 years of records are very, very sparse at high elevations. So there's a database of stations. Out of 7,000, almost 7,300 stations, only 3% of them are above 2,000 meters, and less than 1% are above 3,000 meters, and long-term data is simply non-existent above 5,000 meters in any mountain range. Unlike in the Arctic, which is relatively homogeneous, mountain temperatures suffer from extreme local variability due to factors such as topography, slope, aspect, which way it's pointing, which direction it's pointing, and exposure. Very few of the stations are on isolated peaks and plateaus. Many are within valleys, and in the valleys they get different microclimates depending on cold air drainage. So cold air from up high draining down through the valleys, and that gives, it makes it very hard to do decent measurements. You can do measurements with satellites, but satellites are measuring skin temperature, which is not generally recorded at surface met stations, which are measured